Right. So last time we talked about for concurrency where you need logs, but also proper ordering, condition variables, right? So when you're waiting for some condition to be met, enforced by some other thread, then you need to get some signaling mechanism to know that you can go and execute whatever you need to do. So today, the first half, we're going to talk about semaphores that actually is a form that could actually satisfy both. So thing we're going to try to learn is how can we use semaphores instead of locks and condition variables? How can we define semaphore? And when one form is a binary semaphore, what is it? And how can we build it out of locks and condition variables, or the other way around, can build locks and condition variables out of semaphores. So definition of semaphore is only an object, really. It has an integer value, and we can manipulate with two different routines. One is semWait, semaphore wait, and semPost. So we can simply define as, we include a header, semaphore S, and we need to initialize it. Now the key part here, so S is a semaphore. The third parameter here, 1, means we're initializing to 1. And as we'll see today, what value we put here is very important. Now the second argument here, 0. Now, through our course, this will always be 0. Now, not in all cases this is 0, but within our scope, this will always be 0, which means the semaphore is shared between threads in the same process. Okay, so this one will be 0 for us, and this is the value of 1 is very important, as we'll see. So we have semWait and semPost. So the implementation itself, how we do it, is not important at this moment. So let's just understand what it does. So here, it will decrement the value of semaphore value S by 1. Now, if this value of semaphore S is negative, you just wait. Right? Now, however, if the value of semaphore, when called, if it's 1 or higher, then you just return. Okay, so if you have semaphore wait, if the value of S is 1 or higher, you just return and you just go keep executing. Otherwise, it will cause the caller to suspend execution, and you're waiting for a subsequent post. Right? So you're basically waiting until someone posts. Now, when the value S becomes negative, the magnitude of that value is equal to the number of waiting threads. Okay, because as we decrement, it means there are multiple different threads waiting for some condition to be met. On the other hand, for posts, it doesn't wait for any condition. It simply just increments the value of semaphore S by 1. And if there are 1 or more threads actually waiting for this to happen, then we go ahead and wait one of them. So one form of semaphore is a binary semaphore, which is a lock. Now, for locks, the value of X is 1. So we're going to have various forms of 1 implemented by semaphore. The value will always be 1. The way to remember is a lock, there should be only one lock. Right? So the value here will be 1. So we have a semWait here, and you go do the critical section, and then you post. So let's look at an example here. Now the value of semaphore initialized to 1. Now let's say thread 0 calls semWait, then you decrement the value. and then it returns, you do the critical section, then you post, the value is now back to 1. And if, let's say the next thread wants to use it, you could basically use value 1, so you go get it and you just go execute. Now let's look into a little bit more complex situation. All right. So here, initially, value 1, you call wait, now it's 0. So it basically returns, right? So value 0, so you just return and you go execute the critical section. Let's say while you do it, you get an interrupt. So you go to thread 1. Now this calls sem wait. Now at the time the value is 0, and now it will decrement to -1. So since the value is less than 0, this will go to sleep. Right? So it's basically waiting. So your state changes to sleeping. So you go to sleep, then you switch back to T0. Note here still values -1. So critical section keeps getting executed. Later on, it will do sem post, which increments the value, and now is 0. Right? Since you're done and value 0, you need to wake whoever was waiting for this to happen. So you go wake T1, sem post returns. Now you go back to T1. So now, because the value is 0, sem wait now returns, executes critical section, and then you call sem post, and now value back to 1. So this basically demonstrates that for a lock, you need to initialize this value to 1. And when you have multiple threads, you can still enforce a lock. Now let's look at a different case now using semaphore for ordering or condition variables. Because condition variables is really, at the end of the day, it's really ordering who does what first and then later. So this is a case where a parent waiting for his child. This is an example we've seen numerous times. So for child, it's pretty simple. You just do a post after you're done, basically signaling. Now for the main function, you create a thread, a child thread, then you wait. Now in this case, the question now becomes, what should we initialize the semaphore value with? And when it comes to condition variables, typically 0. And we'll see the case here. Now, there are two cases. As you know, when you create a child thread, depending on scheduling, sometimes the child could be executed first or could be the parent. So let's look at two different cases. Case 1, where the parent creates a child, right? And it's keep getting executed. So you first call sem wait. Now, because initial value is 0, with sem wait, you decrement sem. So now it's -1. Now, as the value is less than 0 itself, the parent will go to sleep. Okay, and then you're switching to the child. Now the child runs. It will do its thing. At the end of child, it just does sem post, which basically increments the value of sem to 0, which will wake the waiting thread. So we'll wake the parent, the return, and then sem wait returns. So in this case where the parent is being executed with the value 0, this works. The other cases where we create a child and then child runs immediately, right? So still value 0, child runs, right? When it's done, it's calling sem post, which increments semaphore to 1. Now, right now, there is no thread waiting for this, right? There's nobody to wake up, which is okay, right? Nobody gets woken up, but the value is still 1. Then sem post would return. And now let's say parents run, right? You created a child went on to execute itself. And now when we call sem wait, we realize the value was 1. So now you decrement. Since the value of semaphore is 0, which is not a negative number, so you're still awake, then you're just done. You return because child has already executed. So again, the initial value for condition variables in semaphore is 0. Now we're gonna go try to solve a few different problems, and we're gonna use semaphores to solve those. So the first one we're gonna look at is the producer-consumer problem, or some people call it the bounded buffer problem. So the producer basically it's a put interface. So you generate something, you put something in a buffer, but it waits for a buffer to become empty. You wait until it's completely empty, then you put it. Consumer, on the other hand, you consume, so you want something in the buffer that you just get, right? So here you can think of, let's say, a buffer size 1, right, to keep it simple. Now for this, a simple code would look like basically you put the value in the buffer, and then you do a modular for index of the fill. Get is basically you get whatever in the buffer, blah, blah, blah. So if you want to actually do this with a semaphore, we're going to define 2 different semaphores. One's called empty, the other's called full, right? Because those are the conditions, each one, right? So producer basically waits until the buffer is empty, then you go fill, right? So here in the producer, you do a semaphore wait for empty, then you post saying, hey, I filled everything up. So semaphore post full. On the other hand, for consumer, it's the other way around, right? So you wait until it's full. When it's full, you just keep getting it. And when it gets empty, you do a post so the producer can go put things in. Now here, when the max is 1, it actually works pretty fine. But if the max is greater than 1 here, when there are multiple producers, the race condition actually could happen, because what we forgot here is mutual exclusion. So the filling of a buffer and incrementing the index into the buffer is actually a critical section, right? You can't have multiple producers do this at the same time. So simply, we need to create a lock, right? So from the previous code snippet, which was not correct, so the way to do it is simply surround a critical section with a lock. So we create another lock, mutual exclusion, mutx. Yes, same thing with producer and consumer. However, this still isn't complete because there's something called deadlock. So let's imagine 2 threads, one a producer, one a consumer. Okay, let's say the consumer first acquires the mutex lock. Then consumer calls sem wait on the full semaphore. Here, line C1. Now, there's no data because producer hasn't filled anything up. Consumer, there's nothing to do. It is the CPU. However, there's nothing, but you still have this lock, right? You haven't given up the mutex lock here because we haven't gotten here. Now then producer would call sem wait, but it's stuck, right? Because he's waiting for the lock. So here, consumer, while having a mutex lock, is waiting for producer to fill up the buffer. Now let's say producer has things to fill up, but doesn't have that lock, right? So it's waiting for each other. So they're both stuck, waiting for somebody else to do things that only you have, but you can't release it, right? So this is a deadlock. So let's talk about deadlock. What are some real life examples of deadlock? Non-computer things. Are you guys thinking, or don't care, or bored, just want to get on with it? Think harder. What's the real, have you ever been in a deadlock? Which problem? Parking. Like, elaborate. So there's a parking spot, one spot available, and all the cars come in different direction. Yes, there's a classical traffic problem as well, right? So everybody can't move until somebody else moves. Right. It's a good one. Anybody else? Yeah. Hopefully a very close friend, yeah. Sort of, yeah. Okay, yeah, makes sense. Yeah, I'll give you one. Since I like to use relationships as examples, because I'm sure most of you have experience with relationships. So how many of you have ever had like romantic relationship? Come on. I mean, how many have you not had relationships? Everybody had relationships? Yeah? Come on, guys. Come on. I mean, I'm not talking technology here. Let's just have some fun. I'm bored too. Okay. It's okay. Anybody been in a relationship? Please raise your hand. Whoever raises a hand get participation points. You remember that. Have you been in a relationship? 3, 4, 5, 6, 7. Only 7 of? Come on, you guys need to get out more. Okay, so 7 of you. Have you ever been in a fight? Yeah. So when you get in a fight, you fight. What happens next? How do you resolve? Yes, but it could be a condition, right? You could say, hey, I will apologize to her only if she listens to me. But then she might say, I will listen to him only if he apologized to me. That's a deadlock, right? That's a relationship deadlock. And who gives in? Who gives in first? That represents the hierarchy of the relationship, which is typical in men. Yes, you're always right, and I'm wrong, right? So you want to avoid deadlocks in relationships too. All right. I was trying to be fun, but I don't think I succeeded. But anyways, so deadlock. So the solution for this is actually quite simple. We just switch terms. So we swap positions here. We only lock before and after put, right? then that will solve this deadlock problem, right? So if you think of a previous scenario, right, if it is empty, you don't hold the lock. The consumer won't hold the lock, right? So you can wait without having a lock, so there will not be a deadlock problem in the previous example. Same thing here, yes, in the main function. Now, since, this is a lock, the value is 1. The next problem is read-writer locks, which actually makes perfect sense because let's say we have a list, concurrent list, and there are many functions we can use. 2 examples would be insert an item on the list, which actually needs a lock, right? Because the adding part is a critical section. You don't want somebody else adding at the same time, right? Makes sense. Or the lookup cases, I'm just looking it up. Right? I'm just reading. I'm not writing, right? So as long as we guarantee no insert is ongoing while I look it up, we can allow many lookups to proceed concurrently, right? If you just want to take a look, go ahead until I actually change the list. So this is called a reader-writer lock. Now, here, obviously for writing, you only want to have a single writer acquiring that lock. Now, the reader is actually an interesting case. There will be a reader who actually acquire a read lock. Now, there could be more readers that will be allowed to acquire that read lock too. However, the writer, because the condition was as long as nothing is being added while the reading is going on, right? So if there are a bunch of readers in there, as a writer, you have to wait until all the readers are gone, right? A writer will have to wait until all readers are finished. So let's try to implement this. Now, first of all, we have a binary semaphore. So this is just a lock, typical lock. Now we're going to have a write lock. Okay, only one writer can have it. And we're also going to have number of readers. So initially, obviously, this is 0. These are locks, so the initial values are 1. For the write lock, very simple. Just to acquire, sem wait, release, sem post. The reader part is actually interesting. So if I want to acquire a read lock, right? First of all, you wait for a lock. You increment the number of readers because I'm going to read. Now, if the count of readers is 1, meaning I am the first reader, right? Then I'm going to do semaphore wait of the write lock. Okay, so this is a special case. If I'm the first, I'm going to do sem wait to write lock, and then you release the lock here so that other readers can also read. In terms of releasing the read lock, I do a semaphore wait of the lock. You decrement the number of readers. Now, if I was the last reader to finish, right? This if clause shows after the decrement, if the value is 0, meaning now I'm the last one to close the door and leave, then you do a sem post of the write block so that writer can go write, right? So while reading, if I'm the first one to read, I'm going to hold that write lock while still releasing the lock so the others can read, right? As long as they're readers, writing is blocked, right? And then the final reader who gets out of there releases the write lock, right? So reader, writer, problem solved by semaphore. However, it has a fairness issue because it'd be quite easy for a reader to starve the writer. So how can we prevent more readers from entering the log once the writer is waiting is something for you guys to think about. The next problem is the dining philosopher. Anybody heard of this problem, the dining philosopher? Nobody? You have? Where did you learn? In your OS class. Okay, good, good. Now, any of you want to have a career in the computer industry? 1, 2, 3, 4, 5, 6, 7. Only, well, 7 is a magic number today. Rest of you, why you're here? So have you, any of you went to interview for a software engineer position? Any of you? You have? What kind of questions did they ask you? Backend, okay, yeah. Oh, okay. So I know Google is not as hot as before, but a lot of people wanted to go work for Google, right? And Google, you know, kind of started the intense coding interview. Think about it. I mean, they're not asking for your, you know, syntax of your program language. They're actually looking for your problem-solving skills, right? Because at the end of the day, everything is a problem that we're trying to solve, right? One of the popular problem is the dining philosopher problem they would ask, right? So typically, the recommendation, if you want to go prepare for a Google interview, is there's actually books out there and a bunch of resources on the web, so you can do it. But typically, most questions will come from your data structure course, algorithms, and operating systems. Yeah. And again, dining philosopher, thank God Subin took the course so she can go ace that interview. And very interesting problem. In reality, there's no application for this, but it's still a very interesting problem. So many people ask you this question because the solution is quite simple. But anyways, if you ever have an interview, job interview, if you get asked about dining philosopher's question, please email me and thank me. As long as you get the answer correct, okay? So let's look this. There are 5, doesn't matter how many, but let's say 5 philosophers. They're sitting around a round table, right? Now, between each pair of philosophers is a single fork, right? So philosopher 1 on its left has fork 1, P2 has F2 on its left, and so forth. Now, the philosophers do only 2 things. One is, since they're philosophers, they should think, right? And when they're thinking, they don't need a fork. Other times, they need to eat. Now, when they eat, they actually need both forks, right? Okay, so that's the setting here. Think, no eat. When you eat, I need both forks. So the problem here now is, how can we make this happen, right? And the key challenge or goal is, first of all, we don't want no deadlock, right? We don't want philosophers to be starving, right? No deadlock, no starving. Also, we want to have high concurrency. If all of them wants to eat, we want them to eat, right? So that's the goal. So basic loop of which philosopher is that for philosopher I, what it'll do is, well, it thinks. Hopefully it thinks a lot. Now, if it wants to eat, it needs to get forks. Then it eats. When done eating, put forks back. Now, we need to have some helper functions because in order to eat, you need both forks on your left and the right. So function left is basically return P. So if I'm P1, I want fork 1. So that's left. Right is, instead is +1, right? If I'm P1, right is I want to get F2. Now, the modular here is for the case of, I'm doing a bad job of moving. if I'm, let's say, P4, right? Because my right is F0, right? So this is the help function. So basically, philosopher P, if it wishes to refer to the fork on the left, simply call left. You want to use a fork on the right, you do call right. Now we're going to need semaphores, and we're going to have a semaphore for each fork. So we have 5 forks and 5 semaphores. So get forks basically is you wait for fork on the left, and then you wait for the fork on the right. Put fork is you put back the fork on your left, and then put back the fork on the right. Right? Make sense? Now this will induce a deadlock because if each philosopher happens to grab the fork on the left, let's say everybody grab their left. Say, let's eat. Bam, I got my left. Now I want something on my right. There's nothing on the right. They're all starving because it's deadlock. So each has something that somebody else wants, but they will not give up until they get something that somebody else has. It's a very classical deadlock problem. And what's the solution, right? So if you get asked on your job interview, say, oh, the solution is quite simple, right? You say it with confidence, with aura, right? Oh, I took that course in operating systems back in 2023. There's this wonderful professor who taught me a very neat solution. Basically, the problem that we had was everybody grabbed left first, right? So if you just make one philosopher grab one on the right, no deadlock, right? So if you're P4, and we're assuming each philosopher knows its index, you grab right, or sem weight right, and then left. Everybody else, left, right. There's no cycle. That's the very quick and easy solution to the dining philosopher problem. So that each philosophers can go eat and think more. Yes, the end of this section actually introduced something called Semaphores that the author introduced. You can go through it quickly. I won't go into details. The only thing that you should note about Semaphore is that it actually doesn't use the value of semaphore to represent the number of waiting threads, because it doesn't have to. Because the value never goes lower than 0. So this actually is easier to implement. And the current Linux system actually uses implementation. So yeah, go check it out.